A fisherman caught a fangtooth fish. This is what scientists found inside. Jake is a 43-year-old man presenting to a marine research laboratory on the coast of California with an unusual catch from his deep-sea expedition. It's 4 a.m. on a cold November morning. Jake and his crew are 200 miles offshore, pulling up their trawl nets from a depth of 5,000 feet, over a mile beneath the ocean's surface. The pressure at this depth is approximately 2,400 pounds per square inch. That's 165 times the pressure we experience at sea level, enough to crush a human skull like a grape. As the net breaks the surface, Jake notices something unusual. Among the typical catch of rockfish and grenadiers, there's a creature unlike anything in his 20 years of commercial fishing. It's roughly 8 inches long, midnight black, with a disproportionately large head and teeth. Teeth that seem far too large for its body, protruding from its jaw even when its mouth is closed, giving it a nightmarish appearance. This is a fangtooth fish, Anoplogaster cornuta. Anoplogaster, from Greek, anoplos, meaning unarmed, and gaster, meaning stomach, a reference to its lack of pelvic fins. Cornuta, from Latin, meaning horned, though in this case, referring to the horn-like teeth. The fangtooth fish possesses the largest teeth relative to body size of any fish in the ocean. Some specimens have fangs so long, they've evolved special sockets in their skull to accommodate them when the mouth closes. But what catches Jake's attention isn't just the creature itself. The fish's abdomen is distended, swollen to nearly twice its normal size. Something is inside it. Something that shouldn't be there at this depth. Jake, having developed relationships with local marine biologists over the years, decides to preserve the specimen and transport it to the UC Santa Barbara Marine Science Institute. Within 6 hours of the catch, the fangtooth is on a dissection table, surrounded by Dr. Elena Martinez and her team of deep-sea biology researchers. Dr. Martinez begins the external examination. The fish shows signs of barotrauma, damage from rapid pressure change. This is expected. When deep-sea creatures are brought to the surface, the dramatic pressure reduction causes gases in their bodies to expand. Eyes bulge, swim bladders rupture, internal organs can be forced out through the mouth. But this specimen is different. The distension isn't from gas expansion. The abdomen is firm, solid. Dr. Martinez makes her first incision along the ventral side of the fish, carefully peeling back the thin, scaled skin. What she finds causes her to pause and call over her colleagues. Inside the stomach cavity, perfectly preserved by the fish's digestive acids and the cold deep-sea environment, is a plastic capsule. Roughly 2 centimeters long, cylindrical, made of what appears to be medical-grade polycarbonate. The discovery raises immediate questions. How did a manufactured object end up in a fish living at 5,000 feet depth? More importantly, what's inside the capsule? To understand the significance of this find, we need to understand the deep-sea environment where the fangtooth lives. The fangtooth fish inhabits the bathypelagic zone, the midnight zone of the ocean. Bathy, from Greek, meaning deep. Pelagic, meaning open ocean. This zone extends from 3,300 feet to 13,000 feet below the surface. Here, there is no sunlight. The temperature hovers just above freezing. The pressure is crushing. Less than 1% of Earth's biomass exists at these depths. Food is scarce. Fangtooth fish are opportunistic predators, feeding on anything they can catch. Small fish, crustaceans, cephalopods. Their enormous jaws can open wide enough to consume prey nearly as large as themselves. Their teeth, while terrifying in appearance, serve a simple purpose. Once something enters their mouth, it cannot escape. In this environment, the fangtooth has developed remarkable adaptations. Their lateral line system, a sensory organ running along each side of their body, can detect minute vibrations in the water from hundreds of feet away. In absolute darkness, this is how they hunt. Dr. Martinez carefully extracts the capsule from the fish's stomach. It shows signs of partial digestion. The outer surface is pitted and cloudy where gastric acids have begun to erode the plastic. But the seal remains intact. The team transfers to a clean room environment. If this capsule contains biological material, contamination could compromise whatever is inside. Dr. Martinez uses a diamond-tip scribe to carefully score the capsule's seal. She applies gentle pressure. It opens. Inside the capsule is a small amount of liquid, perhaps 0.5 milliliters, and what appears to be tissue samples preserved in a saline solution. The liquid has a slight yellow tint, consistent with formalin or a similar preservative. The tissue samples are small, irregular in shape, ranging from 2 to 5 millimeters. Dr. Martinez immediately transfers the samples to a 80°C freezer for preservation while she develops an analysis protocol. The questions are multiplying faster than answers. Where did this come from? Who created it? And why was it at 5,000 feet depth? The team begins their investigation with the capsule itself. Using spectrographic analysis, they determine the plastic composition matches medical-grade polycarbonate used in implantable drug delivery devices. The manufacturing quality is high. This isn't consumer-grade plastic. The threading on the cap shows precision machining. Next, they analyze the preservative liquid. Gas chromatography mass spectrometry reveals it's a buffered formaldehyde solution, specifically 10% neutral buffered formalin. This is standard for tissue preservation in medical and research settings, but it's the tissue samples that provide the real surprise. Under microscopic examination, Dr. Martinez identifies the cellular structure. These are not fish tissues. They're not crustacean or cephalopod tissues. The cells are organized in a complex arrangement, columnar epithelium with mucin-secreting goblet cells. Beneath that, she can see smooth muscle layers and what appears to be nervous tissue with ganglion cell patterns. These are intestinal tissues, human intestinal tissues. Histological staining confirms it. The tissue architecture is consistent with human jejunum, the middle section of the small intestine. DNA analysis provides additional confirmation. Human DNA, and more specifically, the samples contain genetic material from at least 2 different individuals. The implications are staggering. Dr. Martinez contacts the National Oceanic and Atmospheric Administration. Within 48 hours, federal investigators are involved. The capsule is handed over to the FBI's evidence response team. The Fangtooth specimen is retained by the Marine Laboratory for continued study. What the investigation reveals is a story that intersects deep-sea biology with illegal medical practices. The capsule, investigators determine, was part of a medical specimen disposal operation. Several prestigious research hospitals and universities routinely collect tissue samples during surgeries and procedures for research purposes. These samples, after analysis, must be disposed of according to strict biohazard protocols. Incineration is standard, but incineration costs money. A medical waste disposal company, operating out of San Diego, had been contracted to handle this material. Instead of proper disposal, the company had been packaging samples in waterproof capsules and dumping them at sea, dozens of miles offshore, weighted to sink to the ocean floor. The weights, however, were insufficient for the depth. The capsules, instead of remaining on the abyssal plain at 12,000 plus feet, settled at mid-depths, precisely where creatures like the Fangtooth hunt. Ocean currents carried the capsules. Some sank further, some rose, and some were consumed. To understand how the Fangtooth came to ingest this capsule, we need to understand deep-sea feeding behavior. In the deep ocean, food arrives in 2 primary ways. First, through marine snow, a continuous shower of organic debris falling from the upper ocean layers. Dead plankton, fecal matter, molted exoskeletons, and decaying organisms drift slowly downward, feeding the depths below. Second, through large food falls. When a whale carcass or large fish dies and sinks, it becomes a temporary oasis of nutrition. Deep-sea predators have evolved to investigate any disturbance, any unusual object. A capsule tumbling through the water column creates vibrations. To a Fangtooth's lateral line system, it might register as a potential prey item, something struggling, something worth investigating. The Fangtooth would approach from below. This is their typical hunting strategy. As they close distance, they'd open their enormous jaws. Those fangs, each one curved slightly backward, would pierce the capsule's plastic shell as the fish bit down. Unable to release it due to the tooth configuration, the fish would have no choice but to swallow. In the fish's stomach, a fascinating process begins. Fish gastric acid, while less potent than mammalian stomach acid, still has a pH between 2 and 4. The Fangtooth, as a carnivorous predator, produces relatively strong digestive enzymes, proteases to break down protein, lipases to break down fats. These enzymes begin working on the capsule's exterior immediately. But polycarbonate is resistant to acid degradation. At the cold temperatures of the deep sea, around 35 to 39 degrees Fahrenheit, chemical reactions slow dramatically. The capsule would remain largely intact for weeks or even months in the fish's digestive system. The fish cannot expel it. The capsule is too large to pass through the pyloric sphincter, the valve between the stomach and intestine. It becomes what gastroenterologists call a bezoar, a foreign object trapped in the stomach. Bezoar, from Persian padzar, meaning counterpoison. Ancient medicine believed these objects had magical protective properties. For the fangtooth, the bezoar is fatal, but slowly. The capsule occupies space in an already small stomach. The fish can still feed, but its capacity is reduced. Over time, malnutrition develops. The fish's energy reserves, primarily in the form of lipids stored in the liver, begin to deplete. Swimming becomes more difficult, hunting less successful. By the time Jake's net captured this specimen, the fish was likely weeks away from death by starvation. The distended abdomen, initially mistaken for gas expansion, was actually a swollen stomach attempting to accommodate both the capsule and recently consumed prey. The FBI investigation leads to the arrest of 3 executives at the medical waste disposal company. They're charged with illegal ocean dumping, violating the Marine Protection, Research, and Sanctuaries Act. The company faces over $10 million in fines. Multiple hospitals and research institutions discover they've been unknowingly complicit. Their contracted waste disposal was not what they'd paid for. But the story doesn't end with the arrests. NOAA launches a survey expedition to the dump site coordinates revealed during the investigation. Using remotely operated vehicles, they document the ocean floor at depths ranging from 3,000 to 8,000 feet. What they find is disturbing. Over 400 capsules are recovered from a 3-square-mile area. Many show signs of degradation. Some have ruptured, releasing their contents directly into the marine environment. Tissue samples, preserved human cells, and foreign organic material now contaminate this ecosystem. The long-term ecological impact remains unknown. Human tissues contain compounds not naturally present in the deep ocean, pharmaceutical residues, food additives, environmental pollutants absorbed during the person's lifetime. How these affect deep-sea organisms is unexplored territory. Dr. Martinez publishes her findings in the journal Marine Pollution Bulletin. The paper, titled Anthropogenic Medical Waste in Deep-Sea Food Webs, a case study of Anoplogaster cornuta, becomes one of the most downloaded papers in the journal's history. She concludes with a sobering observation. The deep ocean is not a wasteland. It is not an infinite dumping ground. It is a complex, interconnected ecosystem that we are only beginning to understand. Every action we take at the surface has consequences in the depths below. The fangtooth fish that Jake caught lived its entire life in darkness. It hunted by vibration and instinct. It survived in conditions that would kill most life on Earth in seconds. And it died because humans treated the ocean as invisible, out of sight, out of mind. Jake continues commercial fishing, but he's changed his practices. He now reports all unusual catches to marine research organizations. He's testified before the California Coastal Commission about illegal dumping. He says he thinks differently now about what happens beneath the surface. The medical waste disposal company is bankrupt. Its executives face prison sentences ranging from 3 to 7 years. The cleanup operation for the dump site costs taxpayers $23 million and takes 2 years to complete. Dr. Martinez receives a National Science Foundation grant to study microplastic ingestion in deep-sea fish. Her research team has documented plastic particles in 73% of deep-sea specimens collected from the Pacific Ocean. The ocean covers 71% of Earth's surface. More than 80% of it remains unmapped and unexplored. We know more about the surface of Mars than we do about our own ocean floor. And yet, our influence reaches every depth, every corner, every creature. The fangtooth fish that Jake caught carried evidence of our reach. A creature that never saw sunlight, living at pressures that would crush our lungs, in temperatures that would stop our hearts. It died with human tissue in its stomach.